Hello, hello. Hello. Hello, everyone. Hello, can you hear me clearly? Okay. Okay, so good afternoon, everyone. Welcome to the lecture 10. Today, we will be discussing more about the neural networks on sequential data. Okay, so, and before we move to the content, today's content, I will make an announcement regarding the makeup tutorials for the Deepavali. So for this Thursday, we will not have the in-person tutorial. So for those students who have sessions scheduled on Thursday, we will have some online makeup tutorial for you to attend. And you can attend any of those online makeup tutorials at your convenience. And the detailed information regarding the makeup tutorials can be found in the cosmology. Okay, so there is a CSV file in the cosmology. You can find all the informations of the makeup tutorials, i.e. the time, date, and the corresponding TA that you can contact for the makeup tutorials. Okay? But for the student with tutorial sessions on Wednesday, you should still attend the regular in-person sessions. Okay, so those online makeup tutorials are only for those students who have sessions on Thursday. Okay, so this is the announcement that I want to make before we move on to today's content. Okay, so now let's move on. In today's lecture, we will first introduce recurrent neural networks, which we can use to handle the sequential data. Okay, so this is the first part of today's lecture. And the next, we will introduce the self-attention module and transformer architecture, which can be used to handle the sequential data in parallel. Okay, and finally, we will discuss issues in deep learning, such as the overfitting and the vanishing or exploding gradient problem. Okay, so these are the topics that we will discuss in today's lecture. So now let's start with our first part, the first part of today's lecture, the recurrent neural network. Okay, so the title of today's lecture is Neural Networks on Sequential Data. Then the first question you may have is, what kind of data can be treated as sequential data? Okay? The sequential data actually refers to the data that is ordered, and such as the text data. Okay? So this is a sentence. I saw this saw. This is a sentence. The text data, the sentence, is one type of sequential data. So here, if we change the order of the words, the meaning of the sentence may also change. Okay, so that's why the text data can be treated as the sequential data, because the order of the words matters here. Another type of sequential data is the audio data. Okay, so the audio data is sequential, and we also have the video data. Video data is also sequential. The order of frame actually is meaningful. If you change the order of different frame, the content or the meaning of the whole video may change accordingly. So these are the sequential data, and in today's lecture, we will first focus on the text data. Okay? So given this text data, I saw this saw. Okay? And the second saw is just this saw. So this is the saw, and this sentence is I saw a saw. And now our task is to predict whether each of the words is a verb or not. Okay, so this is our task. We need to predict whether each of the words is a verb or not. Then what should we do? How to predict the label for each of the input words? And before we even start building our network, we need to first convert the text data into a representation that can be processed by the computer. Okay? So for the images can be represented by pixels. And then how about text? How to represent the text data in a way that can be processed by computer? One-hot encoding is one of the easiest way to represent our text data. And what is one-hot encoding? So for example, in your data set, there is a word apple. And in one-hot encoding, you can use a vector to represent this word apple. And in this vector, the index of corresponding to the word here, in your data set, apple is the first word, okay? So the first element in this vector will be set as 1. And the remaining elements in this vector will all be zeros, okay? So there is only one element in each of the vector, so that's why we call it one-hot encoding. So for this vector, the length for this vector is actually just the number of unique words in your data set, okay? So for example, in your data set, you have 1,000 words. Then the length of this vector will be 1,000. And for each of the vector, there's only one in your vector. The remaining elements in this vector are all zeros. Okay? And you can use the same way to represent other words in your data set. So for example, cute is the second word in your data set, then the second element in this vector will be set as 1. And you can use the same way to represent all the rest of words in your data set. Okay, so now we can use the one-hot encoding to process our input sentence, and then this kind of vector can then be processed by the computer. Okay, so now move back to our sentence. We saw this saw. Okay, in this sentence we have 4 words. Okay, so we saw this saw. We will use different vector to represent different words. And in this sentence we have 2 saw. Okay, so it means that these 2 vectors for saw are the same. Okay, so the 2 saw are the same because the index of the saw in the data set are the same. Okay, so now we have this type of data representation. Each of the words in the sentence can now be represented by a vector. Now let's move on. We now know how to represent the data. Then how to predict the label for the data. We want to predict a label for each of the words that tell us whether this word is a verb or not. Okay? So a naive attempt is that we can just build a feed-forward neural network. And in this neural network, we have 2 different layers. So this is the weight of the first layer. This is the weight for the second layer. Okay? Then we can use the vectors that we have already know to use them as the input to our neural network. Okay? So now we can start from we. Okay? So the vector that represents we will then be used as the first input to our neural network, and we can use this neural network to predict the label for our V. Okay? So assume that for our current neural network, the label for V is negative, which means V is not a verb. Okay? Then we can use now we know the label for the first word V. We now can move on to predict the label for our second word, saw. Okay? Now we use the vector represents saw as the input and predict the corresponding label for this saw. And we also need to move on to predict the label for the third word, this. And this is a label. And the last saw. Predict the label for the saw. Okay? So now, since these two saw are the same, the vector that we use to represent these two saw are the same. So the output, i.e. the label predicted for these two saw will always be the same because we just use the same neural network to predict the label for all the words. So we use the same weight in the neural network to predict the label. So as long as they are the same word, then they will have the same predicted label. Okay? So now, this is actually a problem. We know that the first saw is a verb, but the second saw, it is not a verb. But if we build a neural network like this and just input our words one by one, we will always predict the same label for these two saw. So this is not a good solution. So the model cannot predict the correct label for both saws. The reason is the input is actually a sentence. And we cannot predict each label independently. We need some contextual information. Okay? Then, in order to extract this type of contextual information, recurrent neural network was proposed. Okay? So now let's have a look at the recurrent neural network, which can help us to extract the contextual information in the sentence. Okay? So this is actually our original model, which takes the one word as input and predict the corresponding label. And we repeat the same step to predict the label for the rest of the word in the sentence. Okay? So this is our original neural network and our original method to predict the label for all different words. Now, in the recurrent neural network, in order to extract the contextual information, we build the connections between different neurons. Okay? So here, we have the H2 and the H1, they are connected. The output of H1 is now used in the prediction for the H2. And the H2 is used when we predict the value for H3. And the H3 is now used when we are trying to predict the value for H4. Okay? So in this way, the contextual information can then be carried into the next time step. Okay? So now let's have a look at this recurrent neural network architecture in detail. In the recurrent neural network, given an input, we want to predict the output, the label Y. Okay? This is our goal. Then in the recurrent neural network, actually, we will combine the information from two different sources. The first source is the input X. The second source is the output generated from the previous time step. Okay? And then we combine this, aggregate these two sources of information together, and then apply a nonlinear activation function to generate the next HT. Okay? So HT is now generated by taking both HT minus 1 and XT as input. Okay? So this is the way that we use to generate the HT. So now HT actually contains the information from the HT minus 1. And the HT minus 1 contains the information from HT minus 2. Okay? So the contextual information is now can be passed to the next time step. Then in order to predict the final label, we need to take the HT as input and use the normal feed-forward layer to predict the label. Okay? So this is the way that we use to predict the label. By using the HT as input, here this HT is actually more informatic in the RNN because now the HT aggregates the data from both XT and the HT minus 1. Okay? And here, the HT minus 1 part actually help us to extract the contextual information. This is the RNN, and if you have a look at this graph in detail, you may notice that this H1 is actually different from the remaining H2, 3, 4, because there's no H0 here. Then how to create a H0 for H1? Because now in order to predict the HT, we need the value of HT minus 1. So now for H1, H1 is the first hidden neuron, and we do not have the previous H0. One way is initialize the H0 as 0 vector. Okay? So we set this H0 as 0. Then we can compute the H1 in the same way as the remaining hidden neurons. Okay, so this is the recurrent neural network. And the recurrent neural network can also be represented in this way. Why it can be represented in this way? It is because that all the weights, same weights, are applied at each time step. Okay? So as you can see in the previous step, so now in the previous slides, we have different time steps, but actually when we are trying to predict the label for each of the input, we are just using the same weight matrix. So this WXH, WHY, WHH are shared across all the different time steps. Okay? So if they are shared, then we can also represent our recurrent neural network in this way. Okay? And this T is the input of different time steps. And then we use the same way to generate a label for each of the time steps. And here the output, the HT, will then be used in the next prediction. Okay, i.e. when we predict the y hat t plus 1, we will then need to use HT. So now this is our recurrent neural network. This is a very simple version of the recurrent neural network. Our recurrent neural network can also be deep. And how to build a deep recurrent neural network? Given some inputs, we can build our first layer in the recurrent neural network, And in this recurrent neural network, the output will then be used as the input of the next RNN layer. And then we can stack multiple different layers together and use the output of the final layer, layer N, to predict the label for each time step. Okay? So our RNN can also be deep. And this is the deep recurrent neural network. And the next type of recurrent neural network I want to introduce is called bidirectional recurrent neural network. So now, how we build the recurrent neural network? So we will use the, so for example, now we start from the time step xt minus 1. And then we will use the output of the step xt minus 1 in the prediction for the step xt. And then we carry the contextual information to the next time step. So this is how we build the vanilla version of the RNN with one layer. Okay? Then why don't we start from a reversed direction? So originally we start, so for example, if in our sentence we have 10 different words in the sentence, and originally we start from 1 to 2 to ... to 10. Now, why don't we start from 10 to 9 to 8 ... to 1? So we process the data in a reversed direction. Okay? This is also okay for us, right? So we predict it is also a doable method. So we predict the label from the last word. And then we continue to predict the previous one, predicted the label for one time step before. So first we use the xt plus 1 as input, and then we use the xt as input. Then in the next step, we use the xt minus 1 as the input. Okay? So now these two recurrent neural network is actually this is our original recurrent neural network. It processes the data from 1 to 10. And this is our new recurrent neural network, which processes the data from 10 to 1. Okay? So now, in the bidirectional recurrent neural network, what we can, we now, in this new recurrent neural network, it can help us to capture the information for the content after xt. So now, if we want to predict the label for xt, by using this new recurrent neural network, we now see all the content that after xt. Okay? Then, in our original recurrent neural network, it can help us to capture the information for the content before xt. Okay? So now, by using these two recurrent neural networks together, we can now see the whole sentence when we are trying to predict a label for yt. Okay? So the bottom one, see the contents before xt. And the top one, see the contents after xt. And now we combine these two together to predict the final y hat t. So now it's different from the previous original version of RNN, which only have one direction. It only captures the information before the time step xt. Okay? So now if we use the bidirectional recurrent neural network, actually we can see all the information, which is more informative, and it is better than the vanilla version of the RNN layer. Okay? So the bidirectional recurrent neural network can help us to capture the information of the whole sentence. And we can also use the same way to predict the label for y hat t minus 1 and y hat t plus 1. Okay? So for now, for each time step, when we predict the label for each input, we can now see the whole sentence before we make the final prediction. Okay? So the bidirectional recurrent neural network is more informative. Okay? So this is our recurrent neural network. And in the next session, I will introduce long short-term memory, LSTM. LSTM is actually just another type of recurrent neural network, and different from the vanilla version of the recurrent neural network, long short-term memory, LSTM, is just the recurrent neural network with gating. Okay? So now let's have a look at LSTM in detail. In the LSTM, we have a memory cell, okay? So which help us to keep the information that we want to use in the future steps, okay? So this is the memory cell help us to memorize some information, some useful information that we may need. And in the LSTM, we have some gates. As I already mentioned that LSTM is RNN with gating. So now in the LSTM, the first gate is the input gate. Second gate is the forget gate. The third gate is the output gate. Okay? So in the LSTM, we have 3 different gates, and they have different functions. We will discuss that later on. Okay? So now let's have a look at the input gate first. Input gate. There are 2 different inputs that used by this input gate. The first one is the input Z. The second one is the signal control the input gate. So let's have a look at this input gate in more detail. So now for this signal control the input gate, Zi, we will apply a nonlinear activation function to this Zi. And the nonlinear activation function we use here is the sigmoid activation function. Okay? So we will apply the sigmoid activation function to the Zi. And as we all know that the value range that can be generated by the sigmoid activation function is within 0 and 1. Okay? So this value actually can help us to mimic close or open the gate. Okay? So if the value, the predicted value is 0, it means that we want to close the gate. If the predicted value is 1, it means that we want to open the gate. Okay? So now we have this signal to predict a value that indicates whether we want to open this gate or close this gate. Okay? Then we have the input. For the input part, we also need to apply a nonlinear activation function to introduce the nonlinearity in our model. And then we multiply these 2 together. Okay? So here, this Zi is used to control that whether we want to use the input data or not. So if this G1Zi is the value that we predicted, and the value is between 0 and 1. If G1Zi is 0, it means that we do not want to use any input data because we set it as 0 and we want to close the gate. Okay? So no input information will then be used later on. If the predicted value is 1, it means that we want to use the original input Z in our later prediction. Okay? So this is our input gate. The input gate, we have a signal which controls whether we want to use this input or not by predict whether we want to close or open the gate. Okay? And now for the input gate, the output for the input gate is A. And in the LSTM, we also have the forget gate. For the forget gate, we have another signal to control the forget gate, to control that whether we want to close the gate to close the forget gate or open the forget gate. Okay, so we have this signal, and again we use the signal activation function, which can predict the value between 0 and 1 to mimic whether we want to close the gate or open the gate. Okay. And for the forget gate, another input is the C. C is the value that we stored in the memory. Okay? So if the predicted value that's generated by this part is 0, it means that we do not want to use any information that kept in the memory. Okay? We want to remove all the information from our current memory. If the predicted value is 1, it means that we want to keep all the information in our current memory. Okay? So this is a signal. The ZF is a signal that controls whether we want to open the forget gate or close the forget gate. Okay? And then the output of the forget gate is B, and the B will then be used as input for our memory. And the memory C, the C is the value that's stored in the memory, and the C will now be updated by A plus B. Okay, so we used A and B to update the C. A is the part of the information from input, which controlled by the input gate. And B is the part of the information from our original memory, and we add these two parts together to generate our new C and update our memory. Okay? So now once we have the updated memory, then we can use the memory as input for our output gate. So now according to the updated memory C, we now need to generate the output. And let's have a look at the output gate. So in the output gate, the input, we have two different inputs as well. One is the signal that controls the output gate. It means that whether we need to close or open the gate depends on the input signal, ZO. If ZO asks us to open the gate, then we will use the C as input and just output the C. C is the value that we kept in the memory. Okay? So here we have another signal to control whether we want to use the value that's stored in the memory as output or not. If the predicted value for this G1ZO is 0, it means that we do not want to generate any output from the memory. If the predicted value of this G1Z0 is 1, it means that we want to use all the information in our memory cell as the output. Okay? So now we have different gates, and the different gate controls different things. In the input gate, we have a signal to control whether we need to open or close the input gate. In the forget gate, output gate, we also have this type of signal to control whether we need to open or close the gate. Okay, so this is actually the basic thing that we need to know about the LSTM. Okay, so now for this part, for this box, this blue box, we know that we have 4 different inputs. The original input Z. The signal, we have 3 control signal. Control signal ZI, control signal ZO, and control signal ZF. Okay? So for this blue box, we have 4 different inputs, but just one output, this output H. Okay, and now we know what will happen within this blue box. Now we can treat this as a black box. And in this black box, we have a memory. And in the memory, we store some information that we want to memorize. Okay, so this is our black box. And this memory cell can also be named as state. Okay, we can also call it state. Then now the question is, what are the Z, ZI, ZF, and ZO? How to generate these signals or this input that we need to use in the LSTM? And the second question is, how to connect different time steps? Okay, so now we just know how to use some input to generate the output. But in the recurrent neural network, we also need to connect the different time steps together. So now we have these two different questions. How to generate the input that we need and how to connect the different time steps together. So now this is our cell, which takes 4 inputs and generates 1 output. And in order to generate these 4 different inputs that we want to use in the LSTM, we need to use the xt. xt is the input of the current time step and ht minus 1. This is actually very similar to what we used in the RNN. In the RNN, we also use the ht minus 1 that generated from the previous time step. In this LSTM, we also need to use this ht minus 1. Okay? And then we need, in the LSTM, in the next step, we need to concatenate these 2 vectors together. And then use this concatenated vector to predict the signals. Okay? So for the first signal, we take the concatenated vector as input and multiply it with some weight matrix to generate the first signal that we need. And similarly, for the next 2 signals, we generated them in the same way. The difference is the weight matrix that we use here. We use different weight matrix to generate different signal. And also for this input zt, we also generate the input zt in this way. We use the concatenated vector as input and multiply it with some weight matrix. And this weight matrix are all trainable parameters in our LSTM. Okay? So now in the LSTM, in order to generate these 4 different inputs, we need to have 4 different sets of weight. Okay? And then in the next time step, similarly, we need to use the ht from the previous time step as input and concatenate with the concatenate the ht with xt plus 1, and then use this concatenated vector as input to generate the signal that we need to use in our black box. And this is our cell. Here in the cell, this ct plus 1 is actually updated based on the original value in our previous ct. Okay? So ct plus 1 is actually generated from the ct. Okay? And then we can create the next output. Okay? So now this is how we generate the signal or the input that we need to use in our LSTM cell and how to connect the different LSTM cells together. Okay, so this is the LSTM architecture. And the LSTM architecture can also be drawn in this way. Hope this is more clear. So these 2 parts are concatenated together and use this concatenated vector as the input for our get gate, input gate, and to generate the input and the input that we need to use in the output gate. Okay? So the same concatenated vector will be used 4 times to create the 4 different inputs that we need to use. And here we can generate the ht and the ct as I have already explained in our previous slide here. Here is how we generate or predict the value for HT and CT. Okay, so this is the process that we need to follow. This is our LSTM, and now let's do a POEV question. Okay, we have 30 seconds left. In the LSTM, we have 3 different gates, and the different gates have different different things to do to control the input gate, control the forget gate, and control the output gate. Okay, time's up. Okay. So for this question, this is our LSTM model. And the question is, which component of an LSTM is responsible for deciding what information to forget? It is just the forget gate. Okay, so the forget gate is responsible to decide what information to forget. The information to forget is to forget the information that we have in the memory cell. Okay, so this is our LSTM part. And now, for the RNN, actually, we now know the basic component to build an RNN model. And we actually have different types of RNN model architecture. We can have one-to-many. So in the RNN model, we can actually take one input and predict the multiple outputs. So here, given the input, we can predict the first output, and then use the first output as the input for the next step, and then generate the next output. Okay, so this is one-to-many architecture. Take just one input, and then we can generate multiple outputs. And the next one is many-to-one. Okay, so we can take multiple input vector and then just predict the one. We can just take the last one as our output, as the last one. We can use this last one time step to predict the final output that we want. Okay, so this is the many-to-one architecture. We also have many-to-many. So many-to-many here, in this architecture, the number of input is exactly the same as the number of outputs. So we will generate one output for each input. This is the many-to-many architecture. We also have another type of many-to-many RNN architecture. Here, this is the difference. The difference between this one and the previous one is that now the number of inputs is different from the number of outputs. And how to achieve this? We need an encoder and a decoder. Decoder takes the output from the encoder as input to predict the value. So this encoder-decoder RNN architecture, you can also treat this encoder as the many-to-one architecture, and then use the final predict the one as the input for our one-to-many architecture, i.e. the encoder. Okay, so now the decoder can be treated as the many-to-one architecture, and the encoder can be treated as many-to-one architecture, and the decoder can be treated as one-to-many architecture. So now we can build a many-to-many architecture by combining these two together. Okay? And we call this as the encoder-decoder architecture. So for the RNN, we have different applications. The RNN can be used in the sentiment analysis by taking the sentence as input and to generate one output. And RNN can also be used in the speech recognition and the video activity recognition. Okay? So RNN have different types of applications. Okay, so I think we can take a short break first, and then we will continue with the next part of today's lecture.
When I talk to people about artificial intelligence, something I hear a lot from non-experts is, I don't understand AI. But when I talk to experts, a funny thing happens. They say, I don't understand AI, and neither does anyone else. This is a pretty strange state of affairs. Normally, the people building a new technology understand how it works inside and out. But for AI, a technology that's radically reshaping the world around us, that's not so. Experts do know plenty about how to build and run AI systems, of course. But when it comes to how they work on the inside, there are serious limits to how much we know. And this matters because without deeply understanding AI, it's really difficult for us to know what it will be able to do next, or even what it can do now. And the fact that we have such a hard time understanding what's going on with the technology and predicting where it will go next is one of the biggest hurdles we face in figuring out how to govern AI. But AI is already all around us, so we can't just sit around and wait for things to become clearer. We have to forge some kind of path forward anyway. I've been working on these AI policy and governance issues for about 8 years, first in San Francisco, now in Washington, D.C. Along the way, I've gotten an inside look at how governments are working to manage this technology, and inside the industry, I've seen a thing or two as well. So I'm going to share a couple of ideas for what our path to governing AI could look like. But first, let's talk about what actually makes AI so hard to understand and predict. One huge challenge in building artificial intelligence is that no one can agree on what it actually means to be intelligent. This is a strange place to be in when building a new tech. When the Wright brothers started experimenting with planes, they didn't know how to build one, but everyone knew what it meant to fly. With AI, on the other hand, different experts have completely different intuitions about what lies at the heart of intelligence. Is it problem solving? Is it learning and adaptation? Are emotions or having a physical body somehow involved? We genuinely don't know, but different answers lead to radically different expectations about where the technology is going and how fast it'll get there. An example of how we're confused is how we used to talk about narrow versus general AI. For a long time, we talked in terms of two buckets. A lot of people thought we should just be dividing between narrow AI, trained for one specific task, like recommending the next YouTube video, versus artificial general intelligence, or AGI, that could do everything a human could do. We thought of this distinction, narrow versus general, as a core divide between what we could build in practice and what would actually be intelligent. But then, a year or two ago, along came ChatGPT. If you think about it, is it narrow AI trained for one specific task, or is it AGI and can do everything a human can do? Clearly, the answer is neither. It's certainly general purpose. It can code, write poetry, analyze business problems, help you fix your car. But it's a far cry from being able to do everything as well as you or I could do it. So it turns out this idea of generality doesn't actually seem to be the right dividing line between intelligent and not. And this kind of thing is a huge challenge for the whole field of AI right now. We don't have any agreement on what we're trying to build or on what the roadmap looks like from here. We don't even clearly understand the AI systems that we have today. Why is that? Researchers sometimes describe deep neural networks, the main kind of AI being built today, as a black box. But what they mean by that is not that it's inherently mysterious and we have no way of looking inside the box. The problem is that when we do look inside, what we find are millions, billions, or even trillions of numbers that get added and multiplied together in a particular way. And what makes it hard for experts to know what's going on is basically just there are too many numbers, and we don't yet have good ways of teasing apart what they're all doing. There's a little bit more to it than that, but not a lot. So, how do we govern this technology that we struggle to understand and predict? I'm going to share two ideas, one for all of us and one for policymakers. First, don't be intimidated, either by the technology itself or by the people and companies building it. On the technology, AI can be confusing, but it's not magical. There are some parts of AI systems we do already understand well, and even the parts we don't understand won't be opaque forever. An area of research known as AI interpretability has made quite a lot of progress in the last few years in making sense of what all those billions of numbers are doing. One team of researchers, for example, found a way to identify different parts of a neural network that they could dial up or dial down to make the AI's answers happier or angrier, more honest, more Machiavellian, and so on. If we can push forward this kind of research further, then 5 or 10 years from now, we might have a much clearer understanding of what's going on inside the so-called black box. And when it comes to those building the technology, technologists sometimes act as though if you're not elbows deep in the technical details, then you're not entitled to an opinion on what we should do with it. Expertise has its place, of course, but history shows us how important it is that the people affected by a new technology get to play a role in shaping how we use it, like the factory workers in the 20th century who fought for factory safety, or the disability advocates who made sure the World Wide Web was accessible. You don't have to be a scientist or engineer to have a voice. Second, we need to focus on adaptability, not certainty. A lot of conversations about how to make policy for AI get bogged down in fights between, on the one side, people saying we have to regulate AI really hard right now because it's so risky, and on the other side, people saying, but regulation will kill innovation, and those risks are made up anyway. But the way I see it, it's not just a choice between slamming on the brakes or hitting the gas. If you're driving down a road with unexpected twists and turns, then two things that will help you a lot are having a clear view out the windshield and an excellent steering system. In AI, this means having a clear picture of where the technology is and where it's going, and having plans in place for what to do in different scenarios. Concretely, this means things like investing in our ability to measure what AI systems can do. This sounds nerdy, but it really matters. Right now, if we want to figure out whether an AI can do something concerning, like hack critical infrastructure or persuade someone to change their political beliefs, our methods of measuring that are rudimentary. We need better. We should also be requiring AI companies, especially the companies building the most advanced AI systems, to share information about what they're building, what their systems can do, and how they're managing risks. And they should have to let in external AI auditors to scrutinize their work so that the companies aren't just grading their own homework.
Okay. So now let's continue with the lecture content. So in the second part of our today's lecture, is related to the self-attention and the transformer. And now let's have a look at some properties of the RNN. So this is our RNN architecture. And the RNN can help us to capture the contextual information from the previous time steps. This is the advantage of RNN. But in the RNN, actually the output at time step t must wait all the previous time steps to complete. And then we can generate the output for time step t. So we need to wait for the t1 to t minus 1 to complete first, and then we can generate the output for time step t. This is not parallelism friendly. Then is it possible to capture the contextual information without waiting for the previous time steps? The answer is yes, and we need to use the self-attention. So the self-attention can capture the contextual information, and we can use the self-attention to predict all the different outputs together without need to wait for the previous time step to complete first. Okay, so now let's have a look at what is attention. So attention, again, attention takes the sequential data as input, and we have this kind of attention layer. Attention layer, the objective of our attention layer is to generate some output with context directly for each of the inputs. Okay? So now this is our self-attention layer, and the output of the self-attention layer, we want it to directly have some contextual information. Okay? And based on this predicted H value with a context, we can then predict the value for the Y's. Okay? So now the question is, how to make sure the output of, so for this H1, how to make sure H1 is with context? Now let's have a look at this self-attention in detail. So in order to make sure the output H1 is with some context, then when we are trying to predict this H1 value, we need to consider all the different inputs. Okay? So if we can take all the inputs into consideration when we are trying to predict the one output, then this output is with context. Okay? Then how to combine these different inputs together to generate one specific output and make this output to become informative? This is what we need to do in the self-attention layer. So in the self-attention layer, we need to check whether the two input vectors, they are relevant or not. If they are relevant, then we may need to extract some information from this. So for example, when we are trying to predict the H1 for X1, and we find that H1 is very relevant to H4, then we need to extract some information from X4 when we predict the H1. Okay? And we also need to check whether X1 is relevant to H3, whether this H1 is relevant to X2. Okay? So we need to check the input vectors to check whether they are relevant or not. If they are relevant, then we may need to use some of the information from input to generate one specific output. Now, the first question is how to measure whether the two inputs are relevant or not. Okay? So here in the self-attention layer, we need to compute something called attention score. And how to compute this attention score? Given an input, we need to multiply this input with some weight matrix to generate a vector Q. And then for the other input, xj, we need to multiply the xj with another weight matrix to generate the vector k. And then we do a dot product to generate create this alpha value. And the alpha value here is our attention score, which can be used to measure whether these two inputs are relevant or not. Okay? So this is the attention score that we use to measure whether these two inputs are relevant or not. And then for this attention score, it is just a scalar. Okay? So now let's have a look at how to make use of the attention score. As I have already mentioned that for the input x, we need to project the input x to a Q1. And then we need, so this is the way we compute the Q1. And we call it query. So query represents the information we want to focus on. Okay? So now our objective is to predict the H1 with context. Okay? So now this H1 is the information that we want to focus on. And we use the X1 to generate the Q. Okay? So Q is generated based on the input X. And the input X is the input that we want to focus on. And we need to generate some K value. So the K value are generated by multiplying the different input Xi with another different weight matrix, Wk. So as we have already mentioned in the computation for the attention score, we need to project Xi to a vector Q, to project the Xj to a vector K, and then do a dot product to predict the attention score. Okay? So now we have the Q and the K. K represents the information associated with each input that can be compared to the query. Okay? So we generate some key, and we use these keys to compare with our query. Okay? And then we use the key and query to compute our attention score. Okay? So this alpha 1, is the attention score for Q1 and K1. And similarly, we can compute the attention score for Q1 and K2, attention score for Q1 and K3, attention score for Q1 and K4. Okay? So now, according to this attention score, we can now know whether these two inputs, they are relevant or not. If the attention score is very high, it means that these two inputs, they are relevant. If the attention score is very low, it means that these two inputs, they are not relevant. So we may not need to use the information from this irrelevant input vector. Okay? And now we have this original alpha, and we need to apply a softmax layer to normalize all the alpha. So after we apply the softmax, the sum of all the alphas will become 1. Okay? So we normalize the sum of all the alphas to become 1. So i.e. now, after the softmax layer, the sum of all the attention score is 1. Okay? So now we have this new, this attention score, alpha 1 prime. And now this attention score can be used to represent whether these two vectors are relevant or not, right? And now, how to use this alpha to aggregate the information? If the alpha 1, 2 is high, then we want to use more information from 2. If the alpha 1, 3 is low, it means that we want to ignore the information that's generated from the input stream. Okay? So now, actually, we can use this alpha 1, 1, alpha 1, 2, alpha 1, 3, alpha 1, 4 as a weight. Then we use the weighted sum to aggregate the information that we can generate from different inputs, right? And in the self-attention, we need to use another weight matrix called WV to generate all the V's. So now we have for each input we have one V, and this V contains the actual information that is retrieved based on the attention score, i.e. the V's are those vectors that we want to aggregate. Okay? So we want to aggregate the information from all V's according to the attention score. Okay? So V's contains the information that we want to keep, and the alphas are the weight, which we can use the alpha and the V together to compute a weighted sum. And the final output H1 is a weighted sum over all the J's. And the weight is just the attention score. Okay? So the self-attention layer actually predicts the weighted sum over different vectors. Okay? So for this one, we want to generate value for H1. And for H1 is a weighted sum over all the VJs. Okay? So now let's do a POEV. So hope this attention layer is not hard for you. Let's do a POEV together first. This should be easy for all of you. I have already mentioned this for a few times. Yeah, okay, then let's continue for this question. Which of the following best describe the output of self-attention module? The self-attention module. So now let's use the H2 as an example to see what we need when we generate the output for H2. Again, now if we want to generate the value for H2, then we need to use the X2 to create a query. Okay? So we need to use the query generated from H2 here to predict all the attention score. Okay? So the attention score is now between this K1, Q2, K2, Q2, K3, Q2, and K4, Q2. Okay? So we compute the attention score for each of the input against the X2. And now, according to the attention score, we need to apply a softmax. Softmax helps us to normalize the data, and then we just do a weighted sum, okay? According to the predicted attention score and the VJ. So VJ is the values that we want to aggregate together, okay? So here, in order to predict the V's, we need to multiply a weight matrix WV with XI, okay? So this is the self-attention to create the corresponding output. Okay, and the answer to this question is a weighted sum of the value vectors based on the attention score, okay? So the final output is just a weighted sum over different value vectors. Okay? Yes, so we have already gone through this. Okay? So now previously we mentioned that for the RNN, we need to wait for the previous time step to complete, and then we can start to predict the value for the current time step t. So we need to wait for t1 to t minus 1 to complete, then we can predict the value for time step t. Now, in the self-attention, do we need to compute so now if we want to compute the value for H2, do we need to wait for the H1 to be computed first and then start to compute the H2? So in the RNN we need, but in the self-attention we don't need, right? So here, if you understand the whole process we used to generate H2, actually you can find out that the computation, if we want to compute the value for H2, actually we do not need to use any information from the H1. Okay? So now let's have a look at this in detail to show that actually all the output can be computed at the same time. So now we know that for all the input, we need to compute a QKV. Okay? So we need to have Q1, K1, V1 for the input X1. We also need to have Q1, K2, V2 for the input X2. And now in order to compute all the Qs, this is the way that we used to compute Q1. So we multiply the weight matrix WQ with Xi in order to compute the Q1. Okay? And actually the rest of the Qs can be computed in the same way. Okay? So we just take the X1, X2, X4, X3, X4 as input, and then we can compute all the values for Qs at the same time by just using this matrix multiplication. Okay? So here, all the X's can be combined into a same matrix. And then we do a matrix multiplication to compute all the Qs. Okay? So now all the Qs can be computed together. And it is actually the same thing for all the Ks and the Vs. So all the Q, K, V can be computed together for all different time steps. Okay? So now we have the QKV, and in the self-attention, we need to use the QKV to compute the attention score. Attention score, we can so for example, now if we want to compute the attention score by using the Q1 as the query, in order to compute the attention score between K1 and Q1, we just need to multiply them together by using this, by using a dot product, and then we can compute the alpha 11, and we can compute the rest of alpha in the same way. In order to compute alpha 12, we just need to multiply the K2 with Q1. And now if we want to compute the alpha 13, alpha 14, we can compute them in the same way. And now you can see that for the alpha 11, we multiply these two together. Alpha 12, multiply these two. Alpha 13, 14, we can compute this in the same way. So for this, yes, so this is how we compute all the alphas by using the Q1 as the query. We can do the same thing by using the Q2 as a query. Okay? So now we use this Q2 as a query to compute the attention score against this Q2. So between this Q2 and the K1, Q2, K2, Q2, K3, Q2, K4. So now these are the attention score that related to the Q2. We use the Q2 as the input query to compute the attention score. And similarly, we can compute all the attention score for Q2 in this way. Okay? So now these are the Ks and these are the Qs. We multiply the K1 with Q2 to generate this alpha 21. Multiply K2 with Q2 to generate alpha 22. Multiply K3 with Q2 to generate this alpha 23. Okay? Then, so now we know how to generate the alphas for Q2, and for the remaining Q3 and Q4, we can compute all the alphas in the same way. Okay? So now these are all the alphas that we need. And these are the K's, these are the Q's. Okay? So the Q's, all the K's can be combined into a single matrix, K transpose. For the Q, similarly, we can combine all the Q vectors into a single matrix and then multiply these two together to generate all the attention score. Okay? So now all the attention scores can be generated at the same time, all together. Okay? So this is our A. And in the self-attention, we need to apply a softmax to compute the alpha prime, A primes. Okay? So this A primes contains all the alpha primes. Okay? And all the alpha primes can be computed together. And in the self-attention, according to the alpha primes, we need to use a weighted sum. Okay? So we need to use a weighted sum to compute the final output. Okay? So now let's have a look how to compute this weighted sum, all the weighted sum together. Okay? So here, if we want to compute the weighted sum for H1, what we need is just these two parts. These are all the V's. These are all the attention score that we need to use in order to create this H1. Okay? So we multiply this. So the first element in the V1, V2, V3, V4 will be multiplied together with A11, A12, A13, A14, and then add together. So this is a weighted sum over all the V's. Okay? So we use all the attention score to compute a weighted sum, and the result is just the H1. Okay? And then for the rest of H's, we can also compute in the same way. So for the in order to compute this H2, H2 is the weighted sum over alpha prime 2j and the Vj. So now these are all the Vj's. So these are all the Vj's. These are all the alpha prime 2j. Okay? And we want to compute a weighted sum over all the different j's by using the alpha as the weight. Okay? So we just need to multiply this alpha in this column with all the v's here. Okay? And then we can compute the H2. And H3, H4 can also be computed in the same way. And now, for this V, all the V's can be combined together to create this V matrix. And this is our A prime. Previously, we have already computed the value for the A prime, and we just need to multiply these two together to create all the output we need. Okay, so these are all the H's we need here. H contains all the output for different time steps. Okay? So now let's have a look at these whole steps together. At the first beginning, we use some weight matrix to generate all the Q's, K's, and the V's together. And according to this QKV, we can then multiply this K transpose and the Q together to generate our A. A contains all the attention score, and use a softmax to normalize the attention score that we generated. And then we can use this A prime, multiply the V with A prime to generate the output H. So here, this output H contains four vectors. So we can generate this H1, this is H2, this is H3, this is H4. Okay? So it means that by using this, how many? 1, 2, 3, 4, 5. 5 weight matrix, 5 matrix multiplication. We can now generate all the H's at the same time. So it means that all the output can be generated together. So we do not need to wait for the H1, H2, H3 to complete before we need to compute H4. Okay? So in the self-attention, we actually can generate all the output at the same time. This is actually better than the RNN. In the RNN, we need to wait for the previous time step to complete first, and then we can predict the value for the next time step. But in the self-attention layer, actually by using just this type of matrix multiplication, we can generate all the outputs together without need to wait for the previous time steps. Okay? So this is the self-attention layer. And the self-attention layer can extract or capture the contextual information by using the weighted sum over different V's. Okay? So by using this type of weighted sum, we are actually aggregate the information from the different input together to generate one output. Okay? So this output is contextual. This output actually contains some contextual information. And now by using this type of weighted sum, we can achieve our goal. We just need to use one self-attention layer, then we can produce output with contextual at the same time. Okay, so this is our self-attention layer. And the self-attention layer has been used in transformer. What is transformer? Transformer is just a deep neural network based on the attention mechanism. Okay, so now we already know how to the process in the self-attention layer. And this transformer is just based on this attention mechanism. And the transformer is a model which can take a sequence as input and then output another sequence. So this is an overall view of the transformer. Okay, so the transformer. So now transformer takes a sentence in English and can translate it into a Chinese. Okay? So the encoder takes a sentence as input and the decoder output another sentence. Okay? So this is the overview of transformer. Okay? And if you look at this part, this transformer contains encoders and decoders rather than just the encoder and decoder. Okay? So it means that actually the transformer is very complicated. We need to stack different encoder and decoders together to create this very deep neural network, which is called transformer. Okay? And this is encoder module. This is the decoder module. Now let's have a look at the encoder module and the decoder module. So now let's have a look at this encoder first. The encoder module contains two main different parts. The first is a self-attention. Self-attention, we already know how to implement or how to compute the output in the self-attention layer. And in the encoder, we have another part, it's a feed-forward. Feed-forward neural network is also, we have already learned the feed-forward neural network. So now, after today's lecture, until now, we know this part. So we know what is self-attention and we know what is feed-forward neural network. But let's have a look at this decoder part. Decoder part, which is different from the encoder part, there is a component called encoder-decoder attention. So what is encoder-decoder attention? It's still attention. So previously, we have the self-attention. Self-attention, we generate a Q, K, V according to the input. Okay? So the source we use to generate a QKV are the same. That's why we call it self-attention. Because the source we use to generate a QKV, they are the same. So the attention is self-attention. So now for the encoder-decoder attention, for the query part, the queries are generated based on the previous decoder block's output. So i.e. here. Okay? So here, this part we use to generate our query. Then for the K and V, for K and V, we generate the K and V based on the encoder output. Okay? So we use the encoder output as the key and value, but use the decoder output as the query. So now, using this type of encoder-decoder attention, actually we can utilize the contextual information provided by the encoder. Okay? So we are trying to combine the information in the encoder and decoders together. Use the information from the encoder to generate the key and the value, and use the information from decoder to generate the query. And why we can utilize the rich contextual information provided by the decoder? It is because we generate the values according to the output of encoder. And in the attention layer is the weighted sum over values. Okay? And now values are generated or created by using the output of the encoder. And then in this encoder-decoder attention layer, we are actually trying to aggregate the values that we generated from the encoder. Okay? So the output of this type of encoder-decoder attention layer is a weighted sum over all the values that we generated according to the encoder. So we can make use of the contextual information provided by the encoder. Okay? So this is the transformer, and the transformer can be used in different applications. So we can use the transformer to predict the next word. So this is actually generative pre-trained transformers, GPT. This is the step 1 in training ChatGPT. Okay? So if we want to train a GPT, we need to provide some input data and output data, and then use the transformer to generate the next word. And in order to train this GPT is very large. In order to train this, actually we need to use a very large data set. Okay? So this transformer takes a sentence as input and predicts the next word by using the transformer. And the transformer can also be used in the vision task. How to use the transformer in the vision task? Transformer it was originally designed to process the sequential information. So now if we want to use the transformer to process a vision task, then we need to first convert input image into different patches and use each patch as one time step. So to make this image to become a sequential data. Okay? So now we have this image. It can be divided into patch 1, 2, 3, 4, 5, 6, 7, 8, 9. And now in order to build a sequential data, our sequential data is now patch 1, patch 2, patch 3, till patch 9. Okay? So we divide the whole image into different patches, and now these different patches can be used to build a sequential data, and then we can use our transformer to handle this sequential data. Okay? So for this vision transformer, we use the image patches as input and then predict the class label. Okay? And this part, we just need the transformer encoder. We do not need decoder, because here we just need to predict one output label. Okay? So this is the vision transformer part. Okay, so then let's move on to the final part of today's lecture, the issues with deep learning. So for deep learning, we might encounter some overfitting problem. In order to tackle the overfitting problem, we need regularization. So in the logistic version, we can use the regularization to prevent the overfit. In the deep learning, we can also design some regularization technique to prevent overfitting. And the second issue in the deep learning is the gradient vanishing or exploding issue. The first regularization technique that we can use is called dropout. Okay? And here, this is our original neural network. This is a feed-forward neural network with some fully connected layer. And this, for the dropout, what is dropout? If we want to use dropout, so during the training, we can randomly set some activations to be 0. So this is dropout. Let's see. So during the training, we can randomly set some activation to be 0. Then in the next iteration, we can randomly set another set of neurons to be 0. Okay? So this dropout can randomly set some activation to be 0 in different time steps. For step 1, we can set neuron 1, 2, 3 to become 0. In step 2, we can set neuron 2, 3, 5 to be 0. Okay? So these are all random. And by using this dropout, we can prevent the overfitting. Why we can prevent overfitting by using the dropout? What is overfitting? Overfitting actually occurs if our model is able to memorize our training data, but cannot generalize to our test data. Okay? So that's why we have this type of overfitting problem. So now if we have dropout, so for every time we randomly drop some neuron, so it is actually introduce some randomness in the data, in the training data, right? And it makes it become more difficult for the neural network to memorize our data set. Okay? So because every time we introduce some we set some neuron to be 0 randomly. So now if we have this type of randomness, then the model, it will be hard for the model to memorize the data. And the dropout encourages the model to learn more robust feature and the meaningful relationship between the input and output data. Okay? Then if we can learn this meaningful relationship, then the model will be able to generalize to the unseen test data. Okay? So this is the dropout. And another technique is called early stopping. What is early stopping? So this is our training loss. This is our validation loss. So after this time, so the loss of the validation set increase, but the loss of our training set still can decrease. It means that our model is now start to overfit to our training data, because validation set is another unseen data. If the loss in the validation set becomes higher and higher, it means that our model cannot generalize to the unseen data. So we can stop here. Okay? So this is the early stopping. So if we find that the validation loss increased after some point, then we can just stop here. And then to prevent the overfitting in our model. And in the deep learning, we also have this type of vanishing or exploding gradient problem. So vanishing gradient, it means that small gradient got multiplied again and again until it reaches at almost 0. Because here, let's use this sigmoid activation function as an example. So for the sigmoid activation function, for this part, the gradient is very small. So the gradient for this part of the sigmoid activation function is very small. And in the backpropagation, if you still remember, in the last lecture, we introduced the backpropagation. We actually need to multiply the gradient that's generated by the later steps together to create the gradient for the previous neurons. Okay? So if we use the sigmoid activation function, this is a sigmoid activation function. The value is between 0 and 1. And the gradient of the sigmoid activation function, what is the gradient of sigmoid activation function? It is sigmoid x times 1 minus sigmoid x. Okay? So if the value for sigmoid x is between 0 and 1, then this sigmoid x times 1 minus sigmoid x, the largest value for this gradient is 0.25. Because this part is between 0 and 1. This part is also between 0 and 1. If you treat this as x, this is 1 minus x. And we know the range of x is between 0 and 1. So the largest gradient for the sigmoid activation function is 0.25. Yeah, so this is very small. And if our neural network is very deep, and for each layer, we use the sigmoid activation function, then our gradient will need to multiply this type of 0.25 value for n times if we have n different layers. N can be very large. So in the end, the gradient will become very, very small. Okay? So for this part, don't need to worry about this part. We will discuss more in the tutorial. Okay? So in the tutorial, we will see why this type of sigmoid activation function is not good. And here I just want to show you that we have this type of vanishing gradient problem. And we also have the exploding gradient problem. If some large gradient got multiplied again and again, then the gradient will become very large. Okay? Then how to tackle this issue? In order to tackle this vanishing gradient problem, we can change to another type of activation function, which is the ReLU activation function. Since this is a ReLU activation function, the gradient for this part will always be 1. It will not be smaller than 1. This is our ReLU. And if we want to deal with the exploding gradient problem, we can just do gradient clipping. So if our gradient is very large, then we just clip it. And then we can solve this exploding gradient problem. Okay? So for this sigmoid and the ReLU part, we will discuss more in the tutorial. Okay? Yeah, so I think that's all for today's content. Let me summarize what we have learned today. In today's lecture, we learned the RNN neural network, and we know how to compute the output for the RNN and LSTM, and some applications of recurrent neural network. And the second part of today's lecture, we learned the self-attention module and the transformer architecture. And lastly, we discussed some issue of deep learning, like the overfitting and the gradient problem. And for the next week, we will learn the unsupervised learning part and the clustering method and some dimension reduction method called PCA. And to do, we have lecture training 10 and also PS40. So PS40 is a small problem set, and it is out now. The deadline is this Saturday. Yeah, so this is a very small problem set, and you can have a look at it after the lecture. Yeah, and that's all for today's lecture, and see you. Bye-bye.